Well, suppose we have a surface defined parametrically like those in the preceding lesson where we had those interesting surfaces defined as vector valued functions, but vector valued functions with two parameters, u and v, multiplying each of the I, j, and k components. So suppose that defines a surface S over some region D, which is the shadow of the surface in the UV plane. Okay, it can be shown that the surface integral of f of x, y, z over the surface S is given by this formula, double integral over surface S, f of x, y, z ds, which is a double integral over the region D, the shadow region, of f of x of uv, y of uv, z of uv. We get that from here, here, and here, times the length of the cross product of the partial derivative of our vector valued function with respect to u and the partial derivative of the vector valued function with respect to v, dA, and we'll do an example in a minute. But notice the similarity to this in the line integral over the path c described by a vector valued function in Unit 5, Lesson 2. Okay, take the time and go back and notice that. It would be probably worth your while. Anyway, how do you calculate such a thing? Well, here it is. Actually, I brought it here, so let's do one. So let our surface S be the first octant portion of the cylinder, x squared plus y squared equals 9. Think about what that says. First octant, x, y, and z are all positive. And x squared plus, or y squared plus z squared equals 9 in the yz plane would be a circle, but x is going from 0 to 4, so it's just that piece of the cylinder up until when x equals 4, the cylinder that would be the circle, except it's not the whole circle because it says in the first octant. More on that later. So we're going to evaluate that integral over that surface S of x plus z ds. And the surface, this is the tricky part, we need to describe that surface in parametric equations. So r of x theta is xi plus 3 cosine theta j plus 3 sine theta k. X goes from 0 to 4. I think it's not too hard for you to see that because that was given. And theta goes from 0 to pi over 2. Now why is that so? That is so because we're only in the first octant of this cylinder. Okay? So that describes our surface in parametric form. Notice that space in there, that the partial derivative with respect to x is just 1, it should be 1i. So maybe there. And the partial derivative with respect to theta of this vector is, well, since the derivative of cosine is negative sine, so negative 3 sine theta, similarly j plus 3 cosine theta k. And so when we look at the cross product of those vectors, we want to say I, j, k in the top. Remember, this is the memory device for that. 1, 0, 0, that's the partial derivative here of rx. R sub x, if you want to call it that, partial derivative of r with respect to x. And the theta, well, we got that filled in here. And evaluating around the I guess you can see what happens is we get 0 minus 0, so that part goes away. Minus j times 3 cosine theta minus 0, so minus 3 cosine theta j. And plus k times negative 3 sine theta minus 0, so here we go. That's it. And so here is our cross product, and the length of that cross product is the square of this plus the square of this and the square root of all that, so we wind up with square root of 9, which is just 3. And our surface integral has become the surface of x plus 3 sine theta, keeping in mind ds, and then the 3 sine theta is what I need to do. That's what's replacing the where is it? Oh, that's what's replacing the z in our integrand. And so x was already the way it was, so x plus 3 sine theta times 3 that we just calculated from the length of that vector, d theta dx. And so this evaluates, and I won't bother you with that because it's too easy to do the evaluation, 12 pi plus 36. So you should verify that, but nonetheless. I mean, here, I'll talk you through it real quick. Integrating with respect to theta, first you get x theta minus 3 cosine theta, theta going from 0 to pi over 2. So you get pi over 2x I guess it would wind up being minus a negative, so plus 3 times the cosine of 0 being 3, so x times pi over 2 plus 3, and then that's also times 3, I forgot about that, so 3 pi over 2x plus, that would then be 9. So then what? Well, then integrate with respect to x, and I'm getting lost in there. Sorry, it may be too much to do by hand, but you should verify that. It's not that hard to do that. So I got a picture of it, believe it or not, of what we're finding. Now, I don't have a picture of the function x plus z as part of it, but that's what we're integrating over this surface here, which I don't know if you can see it from the side here. It's kind of like a quarter cylinder, but it's only 4 units long. So that's that.